Dominion Radio Astrophysical Observatory, located south of Penticton, British Columbia, is home to the John A. Galt Telescope, the Pathfinder Telescope, and the new CHIME Telescope. These telescopes detect radio waves to study the cosmos and help us better understand our galaxy and the universe surrounding us. The Canadian Hydrogen Intensity Mapping Experiment studies pulsars, the expansion of the universe, and a relatively unknown phenomenon known as fast radio bursts.
My name is Alex Hill. I'm an astronomer for the University of British Columbia. I am based here at the Dominion Radio Astrophysical Observatory, where I work on the Canadian Hydrogen Intensity Mapping Experiment.
I'm Richard Shaw. I'm actually a postdoc at UBC, but I spend 4 months a year here at DRAO.
So the CHIME Telescope is the newest radio telescope here in Canada. It was, the first light was in 2017, about a year and a half ago, and it is a really novel new telescope. It's built with no moving parts. It takes advantages of some new technologies, particularly low noise amplifiers, such as are developed for cellular telephones, and graphics processing units, such as are used in video games, but are also very good for the kinds of calculations that we need to make CHIME work. So CHIME started with a few scientists who had an idea, and they tested the idea out at the two-dish array in the yard out behind the observatory, and they did the first tests. And with those first tests, they were able to demonstrate that this basic idea of mapping out hydrogen intensity was basically feasible.
CHIME really started to crystallize. I think there was a workshop held here on new radio interferometers like CHIME, although it didn't exist at that time, in the summer of 2011. A year and a half after that, they started to put together the Pathfinder telescope. We continued building out the Pathfinder, and that was a great platform for testing the new hardware and deploying everything. We've been sort of working on that since, and then not long after, because the money had sort of come in, we had to start figuring out how to design the full thing. And so the Pathfinder was a prototype where we were to be testing instrumentation and learning what we should be doing differently on the full telescope.
We broke ground, I believe, in 2015. Had a big ceremony to say the telescope is starting to work in 2017, and now late 2018, early 2019, the telescope is basically operational now.
The Canadian Galactic Plane Survey studies the gas of the interstellar medium of our own galaxy.
In the late 90s and early 2000s, this observatory was very much focused on constructing a survey of our galaxy called the Canadian Galactic Plane Survey. It used the 7 antennae of the DRAO synthesis telescope, and it observed both the emission from the hydrogen gas and in continuum emission, which is tracing different physical processes, but still related to interstellar gas. And all of these observations have told us a lot about the interaction between stars and gas between the stars. So ultimately, new stars form out of interstellar gas. That interstellar gas gets dense enough so that it collapses under its own gravity until it's dense enough to begin nuclear fusion in the core and form what we call a star, or what we call a main sequence star like our sun. And then ultimately, at the end of their lives, stars return matter and energy to the interstellar medium. So the Canadian Galactic Plane Survey is tracing that process, tracing that cycle, which is fundamentally telling us about where we came from. Because ultimately, we are made, everything except the hydrogen and helium in our bodies, all of the carbon, the nitrogen, the oxygen, the iron, all of the iron that on Earth in particular, all of that was produced by nuclear fusion in previous generations of stars, ejected by those stars into the interstellar medium, and then ultimately, when the sun formed later on, it had those elements that were produced in past generations of stars. So that's fundamentally where we come from. So the Canadian Galactic Plane Survey is an important part of the mix in tracing the cycle of the lives of stars. The idea of CHIME is to get at one of, I think, the really fundamental mysteries in modern physics and cosmology, which is in the late 1990s, astronomers set out to measure how much the expansion of the universe was slowing down over time. You expect, we all have gravity, we in the universe have gravity, so we're pulling the universe towards ourselves, so the expansion should slow down over time. Astronomers looked, and we found that actually the universe is expanding faster over time. We don't really know why, but we know how this effect works. And so we give it a name to parameterize our ignorance with it, which is dark energy.
So that's a big mystery. So indeed, nothing is really known about it. So these days, the observations are, I think, are very robust. That using the cosmic microwave background combined with, usually in combination with other data that comes from the more local universe, like we are very convinced that the expansion of the universe is accelerating. That initially the observations that were very convincing came from supernova in the local universe. So you can use supernova like standard candles and try and figure out how far away different redshifts are in a kind of more physical distance. And if you do this, you see that the expansion of the universe is accelerating as time goes on.
The idea of CHIME is to map out that expansion history in much greater detail than has been possible before, and particularly at a time in the universe when you can't map out the expansion history using any other technique. And by doing so, we will figure out or get a better constraint on how dark energy works, and that will hopefully lead us to figuring out exactly what dark energy is.
From their initial batch of observations with CHIME and looking at the fast radio bursts they got, then they indeed found a second repeating source. So the initial FRBs were all found with parks. The fact that source repeats meant they could actually localize it. So that was all very exciting. So that was the idea of it being a repeating source is very important because in order to look at what mechanism might generate fast radio bursts, a lot of the assumptions was that the process had to be cataclysmic. So the source would essentially destroy itself in the process of emitting the burst. Now, the fact it repeats means that doesn't happen. So the repeater was a bit of an anomaly for a while because there was I don't know the exact numbers, but there was maybe 30 FRBs known, and there was only one repeater. And now CHIME has found a second repeater, and so that tells us a little bit more in that these things are not completely uncommon. And so whether the fast radio bursts we don't see repeat and the ones we do see repeat are completely different classes of source, or whether it's the same source and we're just not quite seeing the repeat bursts from the other sources.
On some level we don't have any idea, but on some level we actually have a reasonable idea the kinds of things that could create these fast radio bursts. In particular, because they're very, very short, they last for about a millisecond. So that means these things have to be really quite compact objects. And the natural candidate for a compact object that puts out a lot of energy would be some kind of compact star. So a kind of neutron star or a stellar black hole. But we still don't know exactly how they're produced. We know of neutron stars and black holes in our galaxy, and they produce brief bursts of radio emission, but they're very regular. They repeat much more than any fast radio burst repeats.
The obvious analog that we have to these kind of things are pulsars. So pulsars basically make very short bursts, but they repeat periodically. Now for FRBs, we'd see them kind of repeat, but it's not regular. So one of the ideas for a long time was that they could be something like a very bright pulsar. There are pulsars which are known which periodically output a burst which is thousands to millions of times brighter than their typical burst. I think that model works mostly if we think the FRB is located in the sort of nearby universe. The other kind of model I think is thought to be quite likely is some kind of emission from magnetars. So magnetars are neutron stars, like we expect pulsars to be neutron stars, but they're extremely highly magnetized. Their magnetic fields are many, many times larger than you would see in a pulsar. And there's, I think, various phenomena which you can have with magnetars, which mean they just release one very bright burst of emission.
As new discoveries are made, CHIME is helping us to better understand the things that surround us in the universe.